All right. Today we're going to learn about the concept of specific heat. By the end of this lesson, you should be able to describe the concept of specific heat, perform calculations with the specific heat equation. And then relating to that, we're going to explain what a calorimeter is and what it does. We're also going to perform some calculations involving a calorimeter, but it's basically going to be the same thing as using this equation over here. So let's talk about what exactly is specific heat. So specific heat of a substance, kind of a technical term here, is the amount of heat energy required to raise the temperature of 1 gram of a certain substance by 1 degree Celsius. It could be any substance. Each substance has their own specific heat. This is slightly different than this term calorie, which is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So you probably heard about calories in food already. In terms of that kind of stuff, that's actually referring to kilocalories. So imagine that times 1,000. Now, let's talk about specific heat in terms of what might actually matter and what you can observe. So if a substance has high specific heat, it is going to be harder to raise or lower the temperature of the sample. More energy needs to be absorbed or released to change the temperature. If a substance has a low specific heat, it is going to be easier to raise or lower the temperature of the sample. Less energy needs to be absorbed or released to change the temperature. So before we even go into an example with numbers, I just want to talk about, let's say, a piece of pizza, right? Here's the crust. I don't know. Here's the cheese. Ooh, cheese, sauce, pepperoni, etc. Now, this piece of pizza is fresh from the oven, and I just want to ask, what is more likely to burn you? The sauce of the pizza fresh out of the oven, or the crust fresh out of the oven? The crust will burn you, or the sauce? What in your mouth will burn you more easily? Okay, let's say the sauce and the cheese are one here, right? But basically, the correct answer should be the sauce, or maybe even the cheese, will more easily burn you than the crust. And the reason for that is because the crust, it's filled up with a bunch of air pockets. There's not that much material that could hold a lot of heat energy in it. So even though the whole pizza might be the same temperature, the crust holds less heat energy than the sauce does. And the reason for that is because of specific heat. The crust would have what we call a lower specific heat, so it has more heat energy in it. And the sauce has a higher specific heat, so it has more heat energy stored in it. Another example we can look at here is water has the specific heat of 4.184 joules per gram degree Celsius. So notice here, it's kind of interesting units there, but that's the units of specific heat. And iron has the specific heat of 0.449 joules per gram degree Celsius. If samples of water and iron with the same mass are put into an oven for 5 minutes, which sample will reach a higher temperature and why? All right, so it looks like water has a larger specific heat than iron. Iron seems to have a lower specific heat. So any guesses here? What do you think will reach a higher temperature first? What will be easier to change the temperature of? Probably the iron. If y'all think about the difference between heating up metals and water, it seems like metals always heat up much faster than water does. So in this case, that relationship holds. The iron will heat up faster because, and our scientific explanation here can be, it has a lower specific heat. And substances with lower specific heats are easier to heat up. Actually, water has one of the highest specific heats of all the substances in our day-to-day lives, which is actually really important for biology reasons. For instance, do you think it's easier for an organism like ourselves to stay in homeostasis when the temperature changes really easily or not so easily? Kind of a complicated question. But do you think it's easier for our bodies to stay in homeostasis if the temperature changes a lot or just a little? just a little, right? So hopefully we have something comprising most of our bodies that tends to not change temperature very easily. And indeed we do. 70% of our body is made up of water, which has a very high specific heat. And it's really hard to change the temperature of things with high specific heat. They just hold so much heat energy per degree Celsius. Is that kind of making sense? All right, let's move on to the next page. All right, so that is the concept of specific heat in general. Let's learn what it means to perform calculations with specific heat. So the calculations that we will perform are done with this equation here. And often I will like to call this equation Q equals MCAT, because here's Q here, there's an M, there's a C, and this kind of looks like an AT. So let's go through the entire equation and I'll talk about what each part means. So Q should be a new concept to y'all. We didn't really talk about it yet, but Q is just a symbol that stands for heat or energy that might be absorbed or released. So whenever we're talking about things that are absorbed or released, I want you to kind of remember, oh, endothermic means when energy is absorbed, and exothermic means that energy is released. Q, since it's energy, it is measured in joules, capital J. Lowercase m stands for mass, it's measured in grams here. The lowercase g is an abbreviation. C is another new term to us. This lowercase c stands for specific heat. So every single substance has its own specific heat. We just saw two examples in the last page with water and iron, but the specific heat here is measured in these units of joules per gram degree Celsius. So basically this means that for every gram of substance and for every degree of Celsius that you change the temperature by, that is how many energy in joules it will take to be absorbed by that substance or be released by that substance to make that change. The final thing here we have is delta T. So this triangle is called delta. It's that Greek symbol for delta or for change. So change in temperature is how you can read this. This temperature change is always measured or calculated in the same way. You always have final minus initial. So the final temperature of whatever is going on minus the initial temperature of whatever is going on. So let's say I have something that starts at 50 degrees Celsius and ends at 100 degrees Celsius. What would be the delta T? So if it is the final temperature minus the initial temperature, I would take that 100 degrees, subtract 50, and get 50 degrees. So that's how I would calculate delta T in that instance. Something else I want to be clear about, let's say I have an initial temperature of 20 degrees Celsius and a final temperature of, let's say, 5 degrees Celsius. So in this case, I'm still going to do final minus initial. So what happens if I do 5 minus 20? I will get something like negative 15 degrees Celsius. So it is possible for your delta T to be a negative temperature value. Okay, and of course, temperature in this class is going to be measured in degrees Celsius. So just going along with all these units here, we do want to say that when heat is absorbed, that is endothermic. The sign for Q is going to be a positive number. Q should be a positive number if you have an endothermic process or reaction. And then the sign of delta T should actually be negative, because the final temperature will be lower if a process is endothermic. When heat is released, we have something that's exothermic going on there. The sign for Q should be negative, and the sign for delta T would be positive, because the final temperature that we measure will be warmer if energy is released into the surroundings. One note, y'all, the only thing that we can measure the temperature of is of the surroundings of our reaction. So we're not measuring the temperature of the system ever, we're measuring the surroundings. So we measure the temperature of the surroundings, not the system. If you stick a thermometer in a cup of water with a reaction happening in there, you're measuring the temperature of the surroundings. Even though the thermometer is right next to the system, it's not inside the system. You can't stick a thermometer directly in a molecule. It's just too small. That's what's going on here. All right, just conceptual thing there. Let's move on to some examples here. This is the meat and potatoes of this lesson. If you're able to solve these types of problems, then you'll be able to do 90% of what the final exam is asking of you. So over here, we do have the situation. A total of 726 joules of heat are absorbed as 128.3 grams of metal is heated from 12 degrees Celsius to 82.6 degrees Celsius. Calculate the specific heat of the metal. All right, we'll type it from. But in terms of this, I'm thinking already, okay, we have grams, we have joules, we have some sort of change in temperature. So I will probably use my Q equals MCAT equation. All right. So over here, I think it would be useful to just kind of list out all of our variables. We have Q, we have M, we have C, and we have delta T. And just remember that Q represents the amount of energy either absorbed or released, and C represents the specific heat that we're looking for here. All right. So over here, we can just start labeling things or filling in stuff that we know about from the question. So I do know that 726 joules of heat are absorbed, so I can use that for Q. That is how much heat energy is absorbed there. For M, I know that the mass here is 128.3 grams of metal. I don't know what kind of metal, but you don't really have to know the kind. Just know that it's one kind of substance there. And then I know my change in temperature is going to equal to my final minus initial temperature. So you could do like T final minus T initial and fill in the numbers for that. In this case, what is my final temperature? I have 82.6 degrees Celsius, exactly. And I will subtract what from it? This 12 degrees Celsius, exactly. Okay, and then we get, what, 70.6 degrees Celsius? I think. I don't know. I did it in my head. All right, sounds good. So we have an equation with 4 variables. We just figured out 3 of them. Can we solve for the last one? Yes. So let's just go ahead and plug in our numbers into this equation. So I'm going to replace all these values that I know about and solve for the one that I don't know about. So in this case, I have 726 is equal to 128.3 times C times 70.6. Okay, so I just put in all the numbers that I know about. And then what I can do now is just some algebra skills. So I'm going to solve this in the way you all are probably most comfortable with. Let's just start simplifying a bit and then try to get C all by itself to see what it is. We're looking for this unknown specific heat. Okay, so on the right side of the equation, maybe I can multiply these 2 numbers together and just kind of put them in front of the C. So I'm going to do that. I'm going to do 128.3 times 70.6. And when I do this, I get some number like 9,058 or so times C. And I still have this equals 726 on the left side. All right, so now that I multiplied those 2 numbers, how do I get C all by itself? I should divide both sides by what number? By the 9,058 to get C all by itself. So that way that cancels out on that C side. All right, so now I can get C all by itself. I just have to perform that calculation on the left side here, where we do 726 divided by 9,058. To get a number, we get 0.0802 or so. And just to be extra correct, let's put the correct units as well. Since we calculate specific heat, this should be joules per gram degree Celsius. I'm kind of squishing it in there, but we just solved the specific heat of our unknown metal. All right, so related question here. We just learned how to do this calculation. Why might this calculation be useful? Let's say we found some metal. We're like, okay, let's perform an experiment on it. Let's see how much heat energy is absorbed by the metal when we heat it up. So we're able to do that now. We just calculate that, and then we can calculate the specific heat. Why might it be useful to calculate the specific heat of the metal? Let me rephrase this question. So do you all remember back to intensive versus extensive properties? Intensive properties were things like density and color, things that didn't matter, like how much you had of something. Extensive properties were things that changed based on how much substance you had, things like grams or volume or height, things like that. So I want you to think about specific heat here. We just calculated this number right here. Do you think this is an intensive property or an extensive property? Do you think the specific heat will change based on the amount of substance we have, or do you think it's inherent to the type of substance we have itself? It's more like, sorry, I use like, I wonder if there's a better word to use, but it's basically inherent. It's like specific to this substance. So this should be specific heat is an intensive property. This is important. I only say this point because I might have seen a question like this on your final. And if something is an intensive property, normally it's very unique to a certain substance. So if something is very unique to a certain substance, that means that we can identify unknown materials. For example, an unknown metal. So since we calculated the specific heat of this unknown metal, and we said, wow, this unknown metal, which I cannot recognize by sight, has a specific heat of 0.08. What if I were to look at a table of all of my known specific heat of metals, and I can see, oh, wait, there's only one metal here that has a specific heat of 0.08. Would that be able to identify your unknown metal? Yeah, if the data matches up, you'd be able to be like, oh, this is obviously aluminum or copper or something like that. And you'd be able to identify that unknown substance just from seeing that the specific heat matches up. Questions so far? All right, let's do another calculation practice. What is the change in heat energy when 38.42 grams of copper at 32.2 degrees Celsius is lowered to 15 degrees Celsius? The specific heat of copper is 0.385 joules per gram degree Celsius. Okay. Once again, this seems like a Q equals MCAT kind of question to me. It's talking about specific heat. It's talking about temperature changes. It's talking about mass of a substance. So I'm going to list out all of my variables and think about what I need to solve for. All right. So my heat energy, I literally don't know that. It's asking for that. My mass looks like it tells me it's 38.42 grams. The specific heat, they do give it to me there. It looks like it's 0.385 joules per gram degree Celsius. And I know my change in temperature is supposed to be my final temperature minus my initial temperature. So which one of these is my final temperature? The 32 or the 15? The 15. So I'm going to do 15.0 degrees Celsius minus the initial temperature of 32.2 degrees Celsius, and then see what we get there. Probably like negative something. Yeah. I feel like I was supposed to be able to do that in my head, but yeah, I got negative 17.2 degrees Celsius as the change in temperature. All right, since we know all of this stuff, let's go ahead and plug it into our equation. The one thing I want to be really clear on is that positive and negative numbers do matter here. So the fact that our change in temperature was a negative number, make sure to bring that negative into the equation. So unknown Q is equal to 38.42 times 0.385 times this negative 17.2. And really the algebra here is very easy. We could just multiply these numbers across and see what we get. Negative something, for sure. If we don't get a negative number, recalculate it. Oops. All right, I'm getting something like negative 254. What are the units for energy here? I should put joules here. So I'm going to put a capital J to represent joules. Q is equal to negative 254 joules. And since I have a negative Q, does that mean energy was released or absorbed? This is energy that was released. So that means that this process was endothermic or exothermic? Exothermic for sure. So energy released, it was exothermic. And that makes sense because we took this copper and we tried to cool it down. The only way you could cool down copper is by taking heat away from it. So heat is being released from the copper to cool it down. Questions so far? All right. We do have, I think, one final concept here. Let's check it out. This is called calorimetry. So you probably already heard about calories in foods, and really they use this word a lot to kind of represent the same thing. All the calories in foods, if you ever wondered exactly how that was actually measured, I'm just going to talk about this for a sec, and you don't have to draw this, but imagine like this really like solid shielded thing. And they might put like a little bit of food in here and close it up and pump it full of oxygen. So they're pumping a bunch of oxygen in there. And then they basically light up this food. And this food is going to basically explode, burn up, ignite with all this oxygen. And then they can measure like, what was the temperature change? And whatever the temperature changed by, they're like, oh, wow, this much heat energy was released by the food. This many calories were released by the food. Why don't we put this on the nutrition label? And that's what they do. So it's not necessarily like how much your body actually digests, but it's pretty close. It's how much energy is released when you burn the food. You can make a really similar structure with a coffee cup. This styrofoam cups there, it's like a good insulator. And the reason why you might want to insulate things is just because you want to measure things like within a certain system itself. So within this water, you might have, maybe some sort of system and surroundings in there, and you could detect the temperature change with a thermometer that you stick in there. So let's talk about this concept in general. What's going on here? Calorimetry is calorimeter is a well-insulated device used for measuring the amount of heat absorbed or released during a chemical or physical process. You can use a calorimeter to determine the amount of heat absorbed or released during a reaction, or you can find the specific heat of an unknown metal, like what we just did a couple practice questions ago. Now, the concept behind a calorimeter still goes back to the law of conservation of energy, where we know that energy cannot be created or destroyed. Energy can only be transferred or transformed. So why might we want to have a coffee cup calorimeter, for instance? So unfortunately, we don't have enough time to do this demonstration right now. But often you can kind of fill up this coffee cup, super easy. Maybe you have double coffee cups for better insulation with some water, and then have some sort of chemical reaction that can happen in water. The reason why we might want to do this is because many reactions happen in aqueous solution or things dissolved in water. So we could do all sorts of things just using coffee cups. When the chemicals react and produce energy or heat energy, the chemical reaction will be exothermic or endothermic? If you're producing heat energy. So if you're producing heat energy, it's like energy is being released. So it's going to be exothermic. And the heat will be absorbed by the solution around the reaction. So because the heat's absorbed by the solution around the reaction, the temperature of the solution will go up or down. If the solution is absorbing a bunch of heat energy, will the solution heat up or go down? It will increase. the solution will get warmer, and you'll notice that the thermometer measures a higher temperature. So if you're measuring an exothermic reaction, heat is released into the area that the thermometer measures, and you measure a higher temperature. When the chemicals react and need heat energy, like they absorb heat energy, the chemical reaction will be endothermic, and the heat will be released from the solution, basically taken from the solution itself. So that means that when you are measuring the solution, the water around this reaction, the temperature of the solution will decrease. So that's how it kind of works in here. So let's kind of label everything that's going on in this calorimeter. I just want to like be clear of what's going on here. So we are measuring with a thermometer. You might also have a stir in there, but lots of times, like if you're setting up something like this, you just kind of stir around the thermometer, and that's usually good enough for a stir. What I will say here is we do have a reaction mixture, but we can say something also like the system is dissolved in the surroundings. And then we could also say the surroundings is equal to the water here. So the water itself is the surroundings. The system would be like something reacting in the water, like maybe some sort of acid and a base. Like, if you were to make a baking soda and vinegar volcano, the surroundings, if this were in the coffee cup calorimeter, would be the water that it's all dissolved in. And in the system would be the actual vinegar molecules and the actual baking soda molecules. Okay. Now the thermometer, if you were to stick it in there, you can only really measure the water. So you're measuring the temperature of the water, but the system is releasing or absorbing energy from the water itself. So you kind of have to think about things in reverse sometimes. But as long as you kind of understand all that going together, hopefully you would not get confused here. All right. Let's look at an example question. A certain food's energy content is analyzed by combusting the food. The mass of the sample of food is 2.34 grams. When this food is combusted, the heat produced heats 1,500 grams of water from 25.8 degrees Celsius to 47.2 degrees Celsius. The specific heat of water is 4.18 joules per gram degree Celsius. Okay. So I'm hearing like food is combusted, the temperature of water like raises. Do you think this process is endothermic or exothermic? So this process will be exothermic. And we'll say it's exo because the combustion of the food, I'll just say combustion, released energy into the water, raising its temperature. So since we measured the temperature being raised, we can say, oh my gosh, that must have been exothermic because energy got released by that food being combusted. All right, and then how much heat is absorbed or released by the solution? Well, we could start doing a Q equals MCAT problem here. So let's try that out. Let's label everything here. Q, M, C, and delta T. It says absorbed or released by a solution. I feel like the solution itself is absorbing energy from like what's being combusted. So let's try to think about this. Let's see. Heat energy, I don't know how much got absorbed. The mass of the solution, well, it says there's 1,500 grams of water. Specific heat of water, they say, is 4.18 joules per gram degree Celsius. The change in temperature of water, it looks like the final temperature is 47.2, and the initial, so we're going to subtract the initial, was 25.8 degrees Celsius. So doing that, we get, let's see, 47.2 minus 25.8. We get like 21.4 degrees Celsius as our change in temperature. Are any questions here so far? All right, so let's go ahead and plug these numbers in. Q, our unknown Q, is equal to 1,500 times 4.18 times 21.4. And if we were to perform that calculation, we would get a number like 134,000. I'll just round it there. 134,000 joules. Yeah, a lot of joules. So since this number is positive, do you think the solution absorbed or released this energy? So the solution itself, like the water, absorbed this energy because it is a positive number. Awesome. I think we just have one more page. All right. So how much heat is absorbed or released by the chemical process itself? All right, so this is a bit of a new concept. We can assume this, y'all. The heat absorbed is just equal to the opposite of the heat released, right? So if our solution absorbed like 130 whatever thousand joules of energy, then that means the chemical reaction released that much energy. So yeah, I forgot the number. Let me look at the number again really quick. The number was 134,000. So 134,000 joules were absorbed or released by the chemical process here. So the solution absorbed this energy. So the chemical process inside the solution must have done what? Released this energy. So this was released. So if we were to write this like as a number in an equation, Q would equal negative 134,000 joules, just to show that that energy was released. All right, we have one more question here. How much heat energy is contained in 1 gram of this food sample? Okay, so I know that there's 134,000 joules in what we just burned. And it looks like what we burned was 2.34 grams. So if we have 2.34 grams, what I can do here is I could take this 134,000 joules, divide it by 2.34 grams, and I can get the amount of energy per gram of food sample. So in this case, 134,000 divided by 2.34 gets us, roughly half. So maybe 57,300-ish joules per gram of food sample. All right. Something like that. All right. Let's do one last example. I'll leave the other one for you to do independently, but using a calorimeter to determine the specific heat of a metal or other unknown chemical. All right, this one's pretty straightforward. We actually kind of know how to do these questions already, but just wanted to let you know if you see a specific example here. Suppose you put 125 grams of water into a calorimeter and find that its initial temperature is 25.6 degrees Celsius. Then you heat a 50-gram sample of the unknown metal to a temperature of 115 degrees Celsius and put the metal sample into the water. Now, the heat is going to flow from the hot metal to the cooler water, and the temperature of the water will rise. The flow of heat stops only when the temperatures of the metal and the water are equal. Both the water and the metal have attained a final temperature of 29.3 degrees Celsius. Now, assuming no heat is lost to the surroundings, like outside of the calorimeter, the heat gained by the water is equal to the heat lost by the metal. And also remember the specific heat of water is 4.18 joules per gram degree Celsius. The other thing to know is the heat of the metal plus the heat of the water is equal to 0. This is just a variation of what we already said before. You could say, oh, the heat of the metal is equal to negative heat of the water. That means the exact same thing. All right, so they're just going to be opposites of each other. The numbers should be equal, but maybe the plus or minus will be different. All right, let's calculate the specific heat of the unknown metal. The thing that we have more information about right now is the water. We know the specific heat of water, we know the mass of water, and we know the temperature changes of water. So let's look at water first and try out this Q equals MCAT equation with water. So let's find out Q, M, C, and then delta T. So for water, we don't know the heat energy yet. We're going to calculate that. For the mass, they said 125 grams of water. For the specific heat of water, notice it's always the same number, 4.18 joules per gram degree Celsius. And for the change in temperature, what was the final temperature of the water? 29.3 degrees Celsius. And what was the initial temperature of the water? 25.6. So let's subtract 25.6 from that and get the change in temperature here. We get like 3.7 degrees Celsius. Okay, so that's our change in temperature. Now we can plug in all of our numbers into this equation, and we have Q is equal to 125 times 4.18 times 3.7. And that's pretty straightforward to calculate. Once we plug that into a calculator, you should get something like 1900 joules as your final answer. Not the final answer. We're still going to calculate the specific heat of the metal. So we can say Q of the water is equal to 1900 joules. So what is the Q of the metal? What's the heat energy released by the metal here? So it's 1900, but it's going to be negative 1900 joules. So we know that relationship. All of the energy that was absorbed by the water should have came from that hot metal. So the hot metal released all the energy into the water. That's how we got that number. All right. So now that we have this number, we can kind of get this. Let's see, what should we do now? We can use the rest of the information that we know about the metal and calculate its specific heat. So this is how many joules that were released by the metal. The other thing that we know is that we have 50 grams of metal, and we should also know the temperature change of the metal. So let's actually go ahead and calculate this with another Q equals MCAT equation. And then kind of define our variables once again. So our Q is equal to negative 1900 joules. Talk about the metal here. Our mass of the metal is 50.0 grams. Our specific heat of the metal, I don't know. We're calculating that right now. And then the change in temperature of the metal. What was the final temperature of the metal? 29.3. And we're going to subtract what temperature from it? The metal. The metal started at 115 degrees Celsius. All right. And that's, if we do this, 29.3 minus 115, you get a number like negative 85.7 degrees Celsius. Okay. So if we plug in all these numbers into the equation, you get something like negative 1900 is equal to 50 times C times negative 85.7. I'm not going to show you every math step here, but once you solve this all, you should get a final answer of like 0.44 joules per gram degree Celsius. And we just solved for the specific heat of this unknown metal that we dunked in some water, okay? All we needed to know is like the mass of the metal, the mass of the water, and then the temperature changes that happen with the metal and the water. With this information, what we could probably do is identify an unknown metal if we didn't already know its identity. All right, questions, y'all? Okay, what I'd like y'all to try out on your own is this problem, perhaps after a brief break. And then you do have your test review stapled to the back of your notes here. So we'll have our test next class period. The expectation is you finish that test review before next class, but hopefully you work on it mostly in this class. Let me end this recording.